In this section, we will be looking at switching characteristics of an SCR. That is, what is meant by switching characteristics of an SCR, why do we need to study it, and a basic introduction to switching characteristics of an SCR when it's turned on. When planning to utilize any object for a purpose, it is a good idea to study how it functions in relation to purpose. That is, let's say we are taking a mobile phone. We can use a mobile phone for different activities. That is, to make a call, to search through internet, to play a game. But for every purpose, the way we deal with the mobile phone is a different one. So you have to know how to do an internet search, how to play a game, and how to make a phone call. Therefore, knowing how it behaves, or in other words, its characteristics, would help us understand why it behaves in a particular manner and how best to utilize it for that purpose. Now, SCRs are used as switching devices, just like our ordinary household switches, to turn on and turn off a supply to a particular part of a circuit. Hence, it is indeed helpful to know how it behaves when it is turned on and off, what are the various currents and voltages involved, and how they vary in relation with each other. Now, this will help us determine what are the do's and don'ts of operating the SCR as a switch. Now, this is very important because if you don't know how we should operate an SCR, it could end up with the SCR being damaged or even the circuit getting damaged. So that is why we have to study the switching characteristics of an SCR so that we can predict how it is going to behave and make the necessary corrections so that it operates in the best possible manner. Now, this behavior of an SCR, this variation of voltage across it and the current through it with respect to time when it turns on and off is known as its switching characteristics. That is, when you turn on an SCR, how the current through it varies and how the voltage across it varies. When you turn off the SCR, how the current varies and how the voltage varies. Now, that study, that variation with respect to time, as the time goes on, how it varies, is known as its switching characteristics. Now, as the characteristics vary with time, it is also known as dynamic characteristics. So, switching characteristics, other name is dynamic characteristics. So, if they ask what do you mean by dynamic characteristics of an SCR, they mean what do you mean by switching characteristics of an SCR. Now, we'll first look at switching characteristics during turn on. Okay. So, our aim while doing this is to understand what exactly is going on when we turn on the SCR. Let's assume that the thyristor is in forward blocking mode. And what do you mean by that? Okay. Let's take a diagram to explain this in a better manner. Now, if you remember the static VA characteristics, we had something like this. So we had something like this, with a shape like this, and then it started off like this. So we are assuming that the thyristor is somewhere here. The thyristor is in forward blocking mode. That is what do you mean by forward blocking mode. That means that anode is positive with respect to cathode. So if you draw a thyristor, so this is anode, this is cathode, and this is gate. Okay. So anode is positive with respect to cathode, but it is not positive enough to be larger than the breakover voltage, forward breakover voltage. So it is somewhere around here. So it is somewhere around here. So it is positive with respect to cathode, but it is not large enough to be over breakover voltage. Moreover, the supply to gate pulse is kept open, that is there is no gate current flowing, so Ig is basically 0. So this is the forward blocking condition. Now this is the condition that we have set up. Now what we do is we give a gate current. We supply a gate current by applying a large enough voltage between gate terminal and the cathode. Now what will happen? Now due to the applied gate current, we have the SCR shifting from forward blocking mode to forward conduction mode. So by applying a gate pulse, by applying a large enough gate pulse, the SCR shifted from forward blocking mode to forward conduction mode. Now what will happen in terms of three values? Let's look at three values. Let's take the gate current. What was the variation in gate current? Initially it was 0 because we have not closed the switch. Most probably how we do is we connect a switch across the gate terminal, and when required we close that switch. So initially the gate current was 0 because the switch was open. Now what will happen? This gate current will build up from 0 to a fixed value, say Ig, the value that being supplied. So this is the variation in the gate current. What happens to the voltage across the anode? Now we are taking this point, okay, we are taking this point and let that voltage at this point. So the voltage at this point is what we are talking about, VA. Now this voltage is high. Why? Because in the forward blocking mode there is a large enough impedance, so that VA will be a very large value, but the moment you apply the gate pulse, what will happen? It will shift to this point. It will shift to this point and VA will fall to the forward on state voltage of the SCR, which is around 1 to 1.5 volt. So the VA shifts from a high value to around this value. Okay. Now what about the anode current? You have to remember that in forward blocking mode there is a very small current flowing from anode towards cathode, and that is known as a forward leakage current. But the moment you close the switch and turn on the thyristor, a large current starts to flow. That is, from forward leakage current, it shifts to an anode current, IA. Okay. This is what is happening when you turn on the SCR, that is when it shifts from forward blocking mode to forward conduction mode. But you can see that although these take place very quickly, these does take some time, and that time for transitioning from forward blocking mode to forward conduction mode, or from turn off to turn on, is known as the turn on time of SCR. Okay. So the time taken from the shift that is occurring from when we apply a trigger to the final completely turned on condition, that time taken is known as the turn on time of the SCR. So that is what is being said here. Let's assume the thyristor is in forward blocking mode, that is anode is positive with respect to cathode, but the voltage applied across the anode is not greater than forward breakover voltage VBO, and no gate current is applied. So that is the condition, that is anode is positive with respect to cathode, so that it is forward biased, but that voltage is not high enough to turn on the thyristor on its own, that is it is not higher than forward breakover voltage. Moreover, there is no gate current supplied. Now in this condition we start the transition from forward blocking mode to forward conduction mode by applying a high enough gate pulse at the gate terminal, which is created by applying a positive gate voltage across the gate terminal and the cathode, most probably by closing a switch. So you will have a secondary voltage. If you remember, you had a secondary voltage that was connected between the gate terminal and the cathode. You simply close a switch so that the circuit gets completed and a positive voltage gets applied across the gate terminal and the cathode. Now this would result in a gate current Ig, which was initially 0 because it was not closed. The switch was not closed, flowing from gate terminal to the cathode, thereby turning on the SCR. When SCR gets turned on, the anode voltage VA, which was high value due to high impedance of the forward blocking mode, falls to a very small value. Now what is that value? That is on state voltage drop. That is around 1 to 1.5 volt. So when you turn on, the voltage falls. The voltage across the anode, voltage across the SCR falls. Moreover, the small leakage current that was flowing from anode to cathode now builds up to anode current IA. All these occur within microseconds of shifting from forward blocking mode to forward conduction mode. So it's very quick. Within microseconds all this happens. From this we can understand that although in the order of microseconds, it does take some time for SCR to shift from forward blocking mode, that is forward off state, to forward conduction mode, that is forward on state. This transition time is called thyristor turn on time. So you can define thyristor turn on time as, it may be defined as the time required by the SCR to change its state from forward blocking mode to forward conduction mode when a gate pulse is applied. Now, although it is a very short time, turn on time can be further divided into 3 parts. Why is that required? This division is important from design point of view. For example, the rise time, which I'll explain in the next video in detail, which is one of the subparts of turn on time, becomes too short or falls below a permissible value, it could end up damaging the thyristor. So we have to control this. So we have to analyze and control this rise time so that it doesn't damage the thyristor. Similarly, every other subsection has some sort of a use. Thus, for understanding and analysis purposes, the total turn on time of SCR is divided into 3 different time intervals: delay time, rise time, and spread time. We'll be looking into these in detail in the next lecture.